Hello, welcome. In the previous week, we discussed vectors in Rn, vector spaces, subspaces of vector spaces, linear combinations, spanning sets, and linear independence and dependence, span of a set. In this part of the lecture, we are going to discuss about basis and dimension of a vector space, dimension of subspaces. Let's begin our discussion with the formal definition of a basis of a vector space. Definition: a set of vectors S containing the vectors v sub 1, v sub 2, all the way up to v sub n in a vector space V is called a basis for the vector space V if the following conditions hold true. 1. The set S spans the vector space V. 2. The set S is linearly independent. So condition 1 means that every vector V in the vector space V can be written as a linear combination of the vectors in the set S. And the condition 2 says the set S is linearly independent, meaning that no vector in the set S is a linear combination of the other vectors in the set S. This definition tells us that a basis has two features. It must have enough vectors to span the space. It should not have so many vectors that one of them could be written as a linear combination of the vectors in it. Example: we want to show that the set S containing these three vectors is a basis for the vector space R3. Let's have a look at the solution. In example 10.2.3 and 10.2.6, we proved that span of S is equal to the space R3, meaning that any vector in the vector space R3 can be written as a linear combination of vectors in the set S. And the set S is linearly independent. Thus, S is a basis for the vector space R3. This basis is called the standard basis for the vector space R3. Geometrically, we can think the first vector in this set S as the unit vector along the x-axis, which is usually written as I hat. Similarly, the second and the third vectors in the set S can be thought of the unit vectors along the y and z-axis, which are usually denoted as j hat and k hat. Similarly, the set S containing the vectors e sub 1, e sub 2, all the way up to e sub n, where e sub n is a vector with n components, with the first component is 1 and the rest of the components are zeros. Similarly, e sub 2 has the second component 1 and the rest of the components are zeros, and so on. The nth vector e sub n has the nth component equal to 1 and the rest of the components are zeros, is called the standard basis of the vector space Rn. In the next example, we want to show that the set S containing these three vectors from the vector space R3 is a basis for R3. In examples 10.2.4 and 10.2.7, we obtained that the set S spans the vector space R3 and S is linearly independent. Hence, S is a basis for the vector space R3. Example 11.1.1 and example 11.1.2 show that basis for a vector space is not unique. Let's have a look at another example. We want to show that the set S containing these four matrices is a basis for M sub 2, 2. Recall that M sub 2, 2 is a set of all 2 by 2 matrices with real entries. This is called the standard basis for the vector space M sub 2, 2. To show that S is a basis, we take an arbitrary matrix with entries A sub 1, 1, A sub 1, 2, A sub 2, 1, A sub 2, 2 from the vector space M sub 2, 2. Clearly, the matrix can be written as a linear combination of these four matrices in the set S. Therefore, the set spans the vector space M sub 2, 2. In other words, span of S is equal to M sub 2, 2. In order to complete the proof, we must show the set S is linearly independent. To show the linear independence, we solve the following vector equation for C sub 1, C sub 2, C sub 3, and C sub 4, where V sub 1 is the matrix 1, 0, 0, 1, and the matrices V sub 2, V sub 3, V sub 4 are as shown. So the left-hand side of the equation takes this form, and the right-hand side is replaced by the zero matrix in the vector space M sub 2, 2. The left-hand side of this matrix equation can be put into a single matrix, and the right-hand side stays as it is. Since these two matrices are equal, we must have C sub 1 is equal to 0, and C sub 2 is also equal to 0, and C sub 3 and C sub 4 are also equal to 0. So the equation we see here is only satisfied for this trivial solution. This shows that the set S is linearly independent. Thus, S is a basis for the vector space M sub 2, 2. Let's have a look at another example. We want to show that the set of these three polynomials, 1, x, and x squared, is a basis for the vector space P sub 2. Recall that P sub 2 is a set of all polynomials of this form: a sub 2 x squared plus a sub 1 x plus a sub 0, where a sub 2, a sub 1, and a sub 0 are real numbers. They can all be equal to 0. Let's denote v sub 1 equals to 1, v sub 2 equals to x, and v sub 3 equals to x squared. Now we take an arbitrary polynomial, a sub 2 x squared plus a sub 1 x plus a sub 0, from the vector space P sub 2. Then obviously the polynomial can be written as a sub 0 times v sub 1 plus a sub 2 times v sub 2 plus a sub 2 times v sub 3. Recall that v sub 1 is 1, v sub 2 is x, and v sub 3 is x squared. This shows that the span of S is equal to the vector space P sub 2, meaning that an arbitrary polynomial from the vector space P sub 2 can be written as a linear combination of these three vectors. For example, if we have a polynomial negative 2x squared plus 4x minus 5 from the vector space P sub 2, then it can also be written as negative 5 times v sub 1 plus 4 times v sub 2 plus negative 2 times v sub 3. Therefore, any polynomial from the vector space P sub 2 can be written as a linear combination of the vectors in the set S. Now, we will show the linear independence of the set S. To show that, we consider the defining equation of linear independence. C sub 1 v sub 1 plus C sub 2 v sub 2 plus C sub 3 v sub 3 equals to 0. If we can show that this equation has the only trivial solution, namely C sub 1 equals to C sub 2 equals to C sub 3 equals to 0, then we will claim the set S is linearly independent. To show that, we replace v sub 1 by 1, v sub 2 by x, and v sub 3 by x squared, and we obtain this equation. This equation is true for all value of x. So, by differentiating both sides with respect to x, we get c sub 2 plus 2 c sub 3 x equals to 0. Again, differentiating, we get 2 c sub 3 equals to 0. So this equation is also true for all value of x. So the last equation gives us c3 equals to 0. And if we substitute this value of c sub 3 into this equation, we get c sub 2 equals to 0. And then if we substitute the values of c sub 2 and c sub 3 into this equation, we get c sub 1 equals to 0. Hence, this equation has the only trivial solution. C sub 1 equals to C sub 2 equals to C sub 3 equals to 0. Thus, the set S of these three polynomials is linearly independent. Hence, S is a basis for the vector space P sub 2.